Hello, and welcome to our first Analytical Foodies bite-sized webinar series. This series will provide hints and tips to help you be successful with your multi-residue analysis. My name is Ewan Ross, and I am a Principal Market Development Manager here at Waters Corporation. The topic of this episode will be chromatographic selectivity. So what is selectivity, and how can we optimize it? In our first bite-sized episode, we talked about the importance of retention, how to calculate it, and to ensure your methods have enough to meet guidelines and give reliable results. In this episode, we are going to consider some column stationary phase and mobile phase parameters that can impact the selectivity of our multi-residue chromatography methods. Selectivity is a capability of a method to distinguish between two or more analytes. It can be impacted by our choice of stationary phase and mobile phase solvents and additives. An example of where selectivity can be important is where we have compounds which are structural isomers, such as subufalazine and terbufalazine. If separation of these two compounds is not achieved by liquid chromatography, the mass spectrometry acquisition method will not be able to distinguish between the two compounds. To calculate selectivity, we need to collect some information on our separation. We initially need the T0, which we explained how to calculate in the episode on retention. We also need the retention times of our two compounds of interest. Once we have collated this information, we can use the following equation to calculate the retention factor, or K, for each of our peaks of interest. We also discussed calculating retention factors in our episode focusing on retention. Once we have our retention factor values, we can then calculate selectivity between our two peaks using the following equation, which gives a ratio of the two retention factors. If we take subufalazine and terbufalazine and calculate the selectivity of the separation shown in this example, then we get a result of 1.02. The value will increase if the separation between the two peaks is improved, or decrease if the peaks are closer to each other. The drawback to this calculation is that it only takes into consideration the peak maxima and does not account for peak width. An alternative approach would be to calculate peak resolution, which considers both retention time and peak widths, such as the USP resolution equation. The method parameters that can change our chromatographic selectivity include our choice of stationary phase, organic solvent choices, and the additives and buffers used to control the pH of our mobile phase. In this episode, we will look at the effects of stationary phase and organic modifier choice on selectivity. The use of C18 columns is common practice for the retention and separation of different pesticide classes in multi-residue methods. There are many different types of C18 columns, and there are retention and selectivity differences between them, depending on the ligand and base particles used. The 4 C18 columns shown here have a range of different characteristics which give them unique selectivities. The Cortex C18 is a solid core particle. It provides high efficiency separations. The other 3 columns are fully porous particles. They include an ethylene bridged hybrid BAH C18, a charged surfaced hybrid CSH C18, and finally a high strength silica HSST3 column. The HSST3 column is a C18 stationary phase technology which has proprietary end capping and optimized pore sizes and ligand densities to achieve optimum characteristics well suited for polar compound retention under reversed phase conditions. To test these columns, a simple gradient using either methanol or acetonitrile has been used to screen the performance of the columns. The additive in this case was 0.1% formic acid. The use of buffers will not be discussed in this episode. However, buffers are often used to control the pH of the mobile phase to avoid shifts in pH which can impact retention of ionizable compounds. And finally, the use of a column manager, as shown, allows for the automated switching of the 4 columns, allowing this screening to be set up and run overnight. In this example, the 4 different C18 stationary phases with the same dimensions have been tested using the same system and mobile phase to monitor the retention of the earliest diluting compound, methimidofos. All 4 columns exhibit retention for methimidofos greater than twice the column void time. The HSST-free column provides excellent retention for this early eluting compound. The choice of organic solvent and reversed phase liquid chromatography can produce different results when analysing compounds on the same column. Common solvents, such as methanol and acetonitrile, will yield different outcomes, and the properties of these solvents should be considered when developing a method. Methanol is a protic solvent, whereas acetonitrile, the stronger of the two solvents in terms of reversed phase elution, is an aprotic solvent. Looking again at methimidofos, you can see that, as expected, when using acetonitrile, the compound elutes earlier on the 4 columns than in the previous slide where methanol was used. Let's look again at the separation between our 2 isomers on each of the 4 columns, using methanol as the organic solvent. Here we can see the 2 compounds exhibit differences in retention and separation, with the HSST-free and the Cortex C18 giving slightly more separation between sirbuphilazine and tertbuphilazine. When using acetonitrile in place of methanol, it has impacted our separation in 2 ways. Initially, as expected, our compounds of interest have eluted earlier. This is not surprising and expected, again with acetonitrile being the stronger elution solvent. However, in this instance, acetonitrile has also given better selectivity between the 2 compounds than observed with methanol. Looking at the different column and organic solvent combinations, differences in selectivity for these 4 compounds are evident. The CSH C18 shows a unique selectivity amongst the 4 columns for compound 4, the fungicide for impropimorph, as a result of the charged surface. As seen in the previous example, acetonitrile has provided the better separation between the 4 compounds. This better separation could allow for greater sensitivity and overall method performance for these compounds. So, in summary, column screening can be utilised to evaluate column stationary phase performance in terms of retention factor, selectivity, and peak shapes. In addition to the screening of stationary phase, the systematic screening of organic solvents, additives, and buffer can offer alternative selectivities to improve peak shape, reduce ion suppression, and improve overall method performance. The process is more efficient when utilising column manager technology. Thanks for viewing this episode on selectivity. More episodes in this bite-sized series are available on waters.com.